Good day everyone. So for today we will be tackling about solutions and their concentrations. So for a solution, that's also known as a homogeneous mixture which contains two or more um, substances, wherein one of those substances will be the solute and regarded as present in smaller amounts, while we have the solvent, um, typically a larger amount within the mixture or solution, and also dissolves the solute. Now there are different types of solutions. One would be on the based on the amount of solute. So for this type of solutions, we have the unsaturated, which means it contains less solute than it has the capacity to dissolve. And then for the other one, we have saturated. Of course, it contains the maximum amount of solute that can be dissolved in a given solvent at a particular temperature or a specific temperature. And then the last one would be the supersaturated, which contains more dissolved solute than is present in a saturated solution. This often results to an unstable solution, and upon cooling down, eventually crystals will form. So in recrystallization processes, this is the main idea, that you will try to obtain a supersaturated solution by increasing the temperature to increase the dissolved solute and then allow it to cool without disturbing, resulting to formation of crystals. And again, before formation of the crystals, upon lowering the temperature, we can consider it as a supersaturated solution. Now we also have a type of solution based on phase. So the phases could either be solid, liquid, or gas. So as you can see on the table, if we have a gas-to-gas solute and solvent mixture, then expectedly the solution would also be gaseous. Then if we have a liquid solvent and a gaseous solute, then expectedly the solution will also be liquid. And if we have a solid solvent and a gaseous solute, then the solution is also expected to be solid. Examples are shown in the last column of the table. Other phases include liquid solutions containing liquid solvent and liquid solute, as well as a liquid solvent and a solid solute. And then the last one would be a solid solution containing both solid solvent and solid solute, which is basically all about alloys, or examples of those are alloys. Now another type will be based on conductance of electricity. Of course, we call a solution to be an electrolyte if it will conduct an electricity. So this means that when the substance or solute is dissolved, for example, in water, and the solution conducts electricity, then we call the solute or the entire solution as an electrolyte. Example for those would be the ionic compounds such as sodium chloride dissolved in water or other salts formed into solutions. So to measure whether a solution is considered to be an electrolyte, we can use a conductivity apparatus wherein electricity will be conducted from the solution using the apparatus, and detection is via the use of a light bulb. So when the light bulb is turned on, in a sense that the conductivity apparatus is submerged in the solution, then the solution is considered to be electrolyte. Opposite is true with non-electrolytes, and this is mainly done with the use of covalent compounds as the solute dissolved in water. Examples would be sugar and alcohol solutions. So using the conductivity apparatus, there will be no electrical conductance occurring, hence the light bulb will not be turned on. Then we have also based on pH, and we define pH as the negative log of the concentration of the hydrogen ion in solution. So if it's acidic, then the pH should be less than 7. If it's basic, it should be more than 7. Okay, so examples are shown in each slide, as you may review later on. And also another one is neutral, which has a pH equal to 7. Mostly these are the neutral salts, and of course distilled water, which is considered to have a pH equal to 7. So in the pH scale, we have here the varying pH values with regards to different products or food products or compounds or substances present. So from most acidic, we have an example there that is gastric acid. It's known to have a pH equal to 1. And then lemon juice contains acids that allows it to have a pH equal to 2. Then followed by apple juice, tomato juice, and black coffee, as well as milk, having still acidic values with a pH less than 7. And again, for pure water, pH is equal to 7, and those that are greater than 7 are considered to be basic, starting with a less basic, that is eggs, and then the concentrated solutions of alkalis such as sodium hydroxide, potassium hydroxide, and so on are considered to be strongly basic. That also includes bleach and ammonia. Now for solutions, of course, we can express them in their respective concentrations, and there are different concentration units of solutions. First one is percent by mass, which is the mass of solute all over the mass of solution times 100, and we can expand this into mass of solute divided by mass of solute plus mass of solvent, since masses are additive, and again solutions are composed of solutes and solvents. Now for a percent by volume, that's the volume of solute divided by the volume of solution times 100. In this case, we cannot expand this to volume of solute plus volume of solvent because volume of the solute and solvents are not always additive. Then we have the percent mass by volume, which is the gram of solute per milliliter of solution times 100, and that's the fixed that's the fixed equation for that particular concentration unit. Aside from that, we have the molarity, which is the moles of solute per liter of solution. It's denoted by capital M. For the moles of solute, if you're given the mass, you can convert it into moles using the molar mass as the divisor. Then we have molality, denoted by small letter m. That's the moles of solute per kilogram of solvent. Take note of the difference between molarity and molality. We're using the liter or volume of solution in liters for molarity, whereas we use kilogram of the solvent for molality. Aside from that, we also have the concept of mole fraction, which is mainly the number of moles of the solute per moles of solution. So it can also be in the form of the number of moles of solvent per total number of moles of solution. The number of moles of solution is equal to the number of moles of solute plus the number of moles of solvent. Another concentration unit would be the ppm or ppb, which means parts per million or parts per billion, which denotes the amount of solute per amount of solution. Specific units will be used, signifying that it could either be ppm or ppb, which will be shown in this table. So for parts per million, if it is in terms of weight by weight of the solute in the solution, then that's milligram per kilogram. Or if it is in terms of the weight per volume of solute and solvent, that will be milligram per liter. And for the volume by volume, that's microliter per liter. For parts per billion, that would be in microgram per kilogram in terms of weight by weight, or microgram per liter in terms of weight by volume, and nanoliter per liter in terms of volume by volume. Now, another thing to learn for with regards to concentrations would be making dilutions. In making dilutions, we actually just increase the amount of solvent to reduce the concentration. So there's an inverse proportionality between concentration and volume for dilutions. As you dilute, you decrease the concentration, but you increase the final volume. And the formula for this is that we have here CIVI is equal to CFVF, where I means initial and F is for final. In the case of dilution, what remains constant is actually the number of moles of the solute. So again, in dilutions, we just increase the volume of the solvent, increasing all in all the volume of the solution and decreasing the concentration. And when you make dilutions, especially in the lab, of course, you need to use the volumetric flask. And if it's in an aqueous solution, then use the wash bottle, which contains the distilled water. So now for examples, we have here how many grams of glucose would you need to prepare 2 liters of 2% glucose mass by volume. So we're given the chemical formula of glucose. That means we can compute for the mass in grams of the glucose, which is taken from 2 liters and 2% mass by volume of the solution. So to solve, we identify first the given. The volume of the solution is 2 liters, or we can transform that one into 2000 ml or milliliters. And the percent mass by volume is 2. Now we can solve for mass of solute, which is in terms of glucose in grams. So that would be percent mass by volume is equal to gram of solute per milliliter of solution times 100. So we can solve for gram of solute. We can then rearrange the formula as gram of solute is equal to percent mass by volume times milliliter of solution divided by 100. So substituting, we have 2 gram per ml, that's coming from the 2%, times 2000 ml divided by 100. So the result, upon cancelling milliliters, would be 40 grams of glucose. Now another example would be how many grams of solute are present in 1.5 liter of 0.2 molar sodium sulfate. So we have here the molarity of sodium sulfate and the volume of the entire solution. Now we need to calculate for the mass in grams of the solute, which is sodium sulfate. So we are given the molarity. That means that's the number of moles per liter solution, or the number of moles of solute per liter solution. So since what's asked is how many grams, then we need to multiply that one after with the molar mass. So before that, we need to solve first the number of moles, which is from the given, we have volume of solution 1.5 liters and molarity, that is 0.2 molar. So to solve for moles of sodium sulfate, or the solute, that's molarity is equal to mole of solute per liter solution. Rearranging, we can solve for moles of solute is equal to molarity times liter of solution. So the molarity can be expanded as 0.2 moles of sodium sulfate per liter solution times 1.5 liters, so that we can cancel out the liter unit. What would remain would be the mole unit. So the result would be 0.30 mole of sodium sulfate. Now, since what's asked is the number of grams of the solute, we can multiply this one with the molar mass of sodium sulfate, which is 142 grams per mole. The 142 grams is based on the values of the individual molar masses of the elements. So we have 2 sodium atoms, or 2 moles of sodium, 23 grams per mole each, so that's 46. Sulfur is 32, and oxygen is 16 times 4, 64. Add those all up, you get 142 grams per mole. Cancel mole and we'll arrive with the grams, which is 42.6 grams of sodium sulfate. Some more examples. We have how many grams of iodine, I2, must be dissolved in 725 ml of carbon disulfide, CS2, which has a density of 1.261 gram per ml to produce a 0.236 molal solution. So to solve for this, we start first with the given. The volume of the solvent is 725 ml, and the density of the pure solvent, which is CS2, is 1.261 gram per ml. Since molality is given as the concentration unit, that is in terms of mole of solute per kilogram of solvent, then we need to transform the mass of the solvent or volume of the solvent into mass of the solvent. So convert volume into mass of solvent. That's mass of solvent is equal to 725 ml multiplied by the density. So that's from the formula, density is equal to mass over volume. So to solve for mass, that's density times volume. So in this case, we have the volume 725 ml and the density of 1.261 gram per ml. We can cancel the milliliter to form 914.225 grams of CS2. Or since we're going to use kilogram of solvent, we can divide it by 1000 to get 0.914225 kilogram of carbon disulfide or CS2. So now we have the mass of the solvent. Now we can compute for the moles of the solute, I2. So we have molality given at 0.236 molal. So we can compute for the moles of solute, which is equal to molality times kilogram of solvent by rearranging the formula. So we have 0.236 mole of I2 per kilogram of CS2 as the expansion of 0.236 molal solution. Then multiply that one with the mass of the solvent, which is 0.914225 kilograms. So then we can cancel kilograms of CS2 or carbon disulfide. We will be left with 0.216 mole of iodine or I2. And since what's asked in the problem is the amount in grams of I2 or iodine, then we can multiply this one by the molar mass of iodine. So the molar mass of iodine is 126.9. There are 2 iodine atoms in the formula, so we multiply it by 2, we get 253.8 grams per mole. We multiply that one with the mole of I2, which is 0.216, and cancel moles of I2. We'll get 54.82 grams of I2 as the mass of the solute. Now some more examples. We have here, how would you prepare 100 ml of 0.4 molar magnesium sulfate from a stock solution of 2 molar magnesium sulfate? So this is an example of a dilution problem. So for the solution, we identify first the given. Again, remember the formula that CIVI is equal to CFVF. So the CI or initial concentration is 2 molar. We know this one for a fact that it's from the stock solution, as well as it is the larger concentration, and we know that the concentration decreases as we dilute. So the final concentration would be 0.4 molar, and the final volume would be 100 ml. That means our initial volume should be less than 100 ml. So to solve this, we use the formula. In this case, we solve for the initial volume, which is CFVF over CI. So substituting the values and cancelling out the molarity units, we should get 20 ml. So that would be the initial volume of the stock solution of 2 molar magnesium sulfate. So to do the dilution, we just need to transfer 20 ml of 2 molar magnesium sulfate, typically using a volumetric pipette, or if not, then you can use also a graduated pipette, making sure to measure all in all 20 ml, and then transfer that in a 100 ml volumetric flask and dilute to mark. So some more examples for dilution. So we have here, you need 250 ml of 0.20 molar sodium chloride, but the only supply of sodium chloride you have is a solution of 1 molar sodium chloride. How do you prepare the solution? So to solve for this, we identify the given initial concentration is 1 molar and the final concentration is 0.2. The final volume is 250 ml. So we can solve for the initial volume, which is CFVF over CI, substituting for the values and cancelling out molarity units. We should get 50 ml, and that would be the initial volume, or the amount in volume of 1 molar sodium chloride to be diluted into 250 ml to form 0.20 molar sodium chloride. So to do this, you need to pipette 50 ml of 1 molar sodium chloride in a 250 ml volumetric flask and dilute to mark.